welcome back to this next video in which we are discussing quotient rings. Okay, so we've now defined multiplication within a quotient ring, and we've shown that this definition of multiplication within a quotient ring is actually well defined. So if I gave the task of multiplying two cosets together to two different people, they would come back to me with the same answer. There is one and only one answer that you can get. Okay, so what we now want to prove then is that this multiplication law actually obeys the axioms of a commutative ring. Okay, so that this quotient ring with this addition and multiplication law on it actually is a commutative ring. Okay, so we need to check 5 axioms then. And we start off with one that's almost identical to the one that we started off with addition, which is closure. So I'll go over the page for this. Okay, so we want to make sure, basically, that if we multiply together two cosets within the quotient ring, that we end up with another coset within the quotient ring. Okay, so axiom number 1, closure. So for all, let's say, A bar and B bar that you can possibly concoct from the quotient ring, so pick whichever A bar and B bar you like from the quotient ring, if we multiply these two together, okay, according to this definition, and let me just straighten it back up again. Okay, so if we multiply A bar and B bar together, and this multiplication will be multiplication in the quotient ring now, so I'll colour that in red there, we need to make sure that the answer is another element of the quotient ring, i.e. that it's another coset. Now again, just as with addition, this is pretty obvious from the way that we have defined multiplication of two cosets within the quotient ring. The way we've defined it is, you take a representative from this one, take a representative from this one, multiply them together in the original ring, get some answer in the initial ring, take the coset that contains that. Okay, you will always end up with another coset when you do it like that, because whenever you multiply two elements of the ring together, that's closed. So implicitly here we are using the fact that multiplication in the initial ring is closed. Okay, so you'll get some other element back in the initial ring, and that will be in one of the cosets, because the cosets have perfectly partitioned up the set that underlies the ring. Okay, so you will always get a coset back as your answer, so the answer will always be within the quotient ring. So that's closure done now. Multiply two cosets together, you'll always get another element back within that set of cosets. Okay, so closure is done. Next, axiom number 2, let's do associativity. Okay, and this follows exactly the same strategy as we approached associativity with addition. Okay, in addition. So let's say for all A bar, B bar, and C bar that you can possibly take from the quotient ring, what we need to prove is that if you multiply these three together, okay, just like we added them together before, that it doesn't matter where you put the brackets, you get the same answer. So either you can put the brackets around A bar multiplied by B bar, and I'll just colour in these multiplication signs because they are multiply in the quotient ring, or you can put the brackets around the B bar multiplied by the C bar. So either you can do it like this, or you can do it like this. So you have the brackets around B bar multiplied by C bar. Okay, so this side means firstly multiply A bar and B bar together to get some coset answer here, and then take that coset and multiply it by C bar, whereas on this side it means firstly multiply B bar and C bar together, get some answer, and then take A bar and multiply it with that answer. Okay, and those two different ways of doing things have to give the exact same answer, and that is multiplicative associativity. Okay, so how are we going to prove that this is true no matter what A bar, B bar, and C bar you pick from the quotient ring? Well, it's going to follow because associativity holds for multiplication in the initial ring. Okay, so exactly the same as the reason associativity held true for addition on the quotient ring, which came from the fact that associativity held true for addition on the initial ring. Okay, so how are we going to do this? Well, we're just going to take the left-hand side, take the right-hand side, develop them a little bit more, and show that they're equal to one another. Okay, so let's begin with the left-hand side. So if we do the left-hand side, firstly we'll multiply a bar with b bar. So we'll take a representative from a bar, we'll take a, we'll take a representative from b bar, we'll take b, we'll multiply them together in the initial ring, and then take the coset that contains that. So this multiplication now is multiplication in the initial ring, so I'll colour it in green there. We now have a coset as our final answer here, and we want to multiply that coset now by c bar. So this multiplication is still in the quotient ring. And the way that we'll do this is we'll just take a representative from here, take a representative from here, and multiply them together in the initial ring. Now the representative we take from here might as well be a multiplied by b. So we take a times b in the initial ring, so I'll colour that in green here. And then we're going to multiply that with our representative from c bar, and our representative from c bar might as well be c there. So here then is our representative of the final answer coset, so we'll take the coset that contains this. So taking the left-hand side, we go from this to this. Okay, now let's develop the right-hand side a little bit more, and of course we're going to get to exactly the same thing, but the brackets will be in a different position. Okay, so multiplying b bar and c bar together, we'll multiply b and c together. Okay, those are our chosen representatives from b bar and c bar. Okay, and take the coset that contains that, and then we'll want to multiply a bar with this coset here, and that will still be multiplication at the moment in our quotient ring. Okay, so to perform that, we'll take a representative from here and a representative from here, so we'll have a from here and we'll multiply it with b times c. Okay, and again I will stress we don't need to worry about what happens if you use different representatives, because we've already shown that it's well defined, so it doesn't matter. You get the exact same answer. We've proven that you will have to get the exact same answer. Okay, so we don't need to worry about that. So we'll perform all of these multiplications in the initial ring and then just take the coset that contains that. So this is what the right hand side is equal to. But of course these two cosets are exactly equal to one another, because a times b with the brackets around it times c in the initial ring is exactly equal to a times b times c with the brackets around it in the ring, because multiplication in the initial ring is associative, and therefore this element is exactly equal to this element. So you're saying take the cosets that contain the exact same element here, and therefore those two cosets are exactly equal to one another. Okay, so that's how we prove multiplicative associativity, and it's just the same proof as we used for addition. We've just replaced the addition signs with multiplication signs rather than addition signs. Okay, so next up, we want to prove that there is a multiplicative identity. So again, be inspired by the way that we approach this for addition. Okay, so what do you think is going to be the multiplicative identity in our quotient ring? Well, it's going to be the coset that contains the multiplicative identity from our initial ring. It's going to be 1 bar. Now, careful here, because you might be inclined to say, oh, well, isn't 1 going to be in the ideal, so isn't this going to be the same as 0 bar? No, 1 doesn't have to be in the ideal. If you remember back to the video on homomorphisms and ideals, any ideal that contains 1 contains the entire ring. Okay, so in fact, any ideal that contains 1 is the entire ring. So there's only one ideal that contains 1, and that's the entire ring. So any proper ideal, any other ideal apart from the entire ring, does not contain 1. So it's not necessary at all that 1 is in the ideal. Remember, an ideal is not a sub-ring. Okay, it's closed under multiplication, but it does not obey the axioms of a sub-ring necessarily. So 1 does not need to be in the ideal. Okay, right. So our multiplicative identity then in our quotient ring is going to be the coset that contains the multiplicative identity from the original ring. Okay, so it's going to be the coset which we might call 1 bar here. Now let's just prove that 1 bar is indeed going to be the multiplicative identity in our quotient ring. So what we need to prove is that 1 bar will multiply by a bar to give a bar back again, no matter what a bar is equal to, and that a bar times 1 bar will equal a bar. So either way round that you multiply them, it will just give the other thing back again. And this multiplication here is done in our quotient ring, so this means quotient ring multiplication here. Okay, so this is very, very simple to prove. all we do is use the definition of multiplication in the quotient ring. So if we want to multiply these two cosets together in the quotient ring, we take an element from here, an element from here. We might as well take the multiplicative identity from the original ring from this coset. So we'll take 1, multiply it by a. When we multiply 1 and a together in the initial ring, we'll get a back again, and therefore the answer will be the coset that contains a, and of course that's just a bar again. And the exact same argument holds true the other way around. So here is going to be our multiplicative identity in the quotient ring. It will be the coset that contains the element 1 from the initial ring. And again, don't worry about what if we used a different representative from this coset that contains 1 to do these calculations. We know that it's well defined, so the coset that you would end up with is exactly the same. So don't make things harder than they need to be. Just use well definition and then pick the easiest representatives you can possibly pick in order to actually do the computation. Okay, right. So axiom number 4 then. We're doing ring theory, so we're not insisting on there being multiplicative inverses for all non-additive identity elements. So that's not axiom number 4. Axiom number 4 now is the two distributivities, left distributivity and right distributivity. So we want to prove that multiplication in our quotient ring is going to distribute over addition in our quotient ring. Okay, so what we want to prove then is for all a bar, b bar and c bar that you can possibly pick from your quotient ring, that it is the case. Firstly, I'll write out left distributivity here. So I'll put the symbols explicitly here. So a bar multiplied by b bar plus c bar. Okay, and I'll just colour these in. So this is multiplication in our quotient ring, and this is addition in our quotient ring. We want to prove that this is going to be the same as if you take a bar multiplied by b bar, and I'll put a bracket around those two, and add it to a bar multiplied by c bar. Okay, and this is all multiplication in the quotient ring. Okay, so that's left distributivity. Right distributivity just has the a bar on the other side. Okay, I'll write that one out as well. We'll only prove left distributivity because right distributivity follows the exact same proof, basically just with minor trivial modifications. Okay, so we'll just prove one of these, but it's obvious then how to prove the other. So this case, b bar plus c bar and then multiplied by a bar, we want to prove that it's going to be equal to b bar times a bar plus c bar times a bar, like so. So we want to prove, again, that multiplication distributes over addition. So this is left distributivity because the multiplication is on the left, and this is right distributivity because the multiplication is on the right. Okay, so we want to prove that this is the case. So we will prove it for left distributivity, and then the proof for right distributivity is exactly the same with trivial modifications. Okay, so let's just examine more what left distributivity actually means. It means that you can either firstly add the two cosets together to get some answer, so your answer coset here, and then take a bar and multiply it with that answer coset to get some final coset. Or you can do it this other way. You can firstly multiply a bar with b bar and multiply a bar and c bar to get two answer cosets here, and then add those two answer cosets together finally. Okay, so these are two very different ways of doing it, and it's not trivial at all that that is going to be true. Okay, but it is going to follow very nicely from the way that we have defined addition and multiplication on this quotient ring, and in fact all it's going to become is that distributivity needs to be true in the initial ring, as indeed associativity and commutativity also become apparent just because of the fact that they are true on the initial ring. Okay, so how are we going to prove this then? So again, we're just going to take the left-hand side, take the right-hand side, develop them a little bit more, and see that they are going to be equal to the same thing. So let's start with the left-hand side here. So we're firstly going to add b bar to c bar, and the way, of course, that we'll do that is we'll take a representative from b bar, take a representative from c bar, add them together, so we'll take b plus c here, and then take the coset that contains the two of them added together. Okay, so this is now addition in the initial ring. Okay, then what we want to do is multiply a bar with that coset that contains b plus c. Okay, so this is still multiplication in the quotient ring here. And of course the way that we'll do that is we'll take a from the initial ring, which we'll use as our representative from A bar, and we'll multiply it by a representative from this coset, and of course we'll pick as our representative B plus C. So the final thing we'll end up with is A times B plus C, where the addition here is done in the initial ring, and the multiplication there, although I haven't written the symbiote explicitly, I'll put a blob there to show that that's multiplication. That multiplication is also done in the initial ring, and we'll take the coset that contains that answer. Okay, so this is our final answer here. Now, what of course we could do here is apply distributivity to that, but we'll wait a little bit to do that. Okay, so now let's develop the right hand side before we actually do apply distributivity in the initial ring to split that up. Okay, so if we look at the right hand side here, let's develop that a little bit. So we want to firstly multiply A bar and B bar and A bar and C bar together. So if we multiply A bar with B bar, we take a representative from A bar, representative from B bar, multiply them together in the initial ring, we'll take A and B here, okay, and that will be multiplication in the initial ring there, and then take the coset that contains that. So that's the answer to this portion, and then we want to add that to the answer to this portion, and the answer to this portion is take a representative from A bar, take a representative from C bar, and add them to, multiply them together in the initial ring, okay, like so, and then take the coset that contains that answer. And then what we want to do is add these two cosets together in our quotient ring, so that's still red addition there. And now if we're going to add these two cosets together in the quotient ring, then of course we just take a representative from here, take a representative from here, add them together in the initial ring. So we'll have A times B as our representative from here, and we'll be adding it to our representative from here, which will take as A times C. Again, we don't have to worry that we're picking and choosing our representatives because everything is well defined. Okay, so we don't need to worry about what happens if you pick other representatives. And then we'll just take the coset that contains that massive great thing, and I will remind you that all of these multiplications and additions, they're all done in the initial ring now. So now, these two things are equal to each other because of distributivity in the initial ring. We can apply distributivity in the initial ring to this, and it will make it into exactly this. So this representative and this representative are the exact same element of the initial ring. So you are asking for the coset that contains the exact same element of the initial ring, and therefore you are certainly asking for the same coset. So these two cosets are absolutely equal to one another, and that's why you can conclude that left distributivity is true in our quotient ring. Now, right distributivity follows exactly the same proof. All you'll use then is right distributivity in the initial ring rather than left distributivity in the initial ring, which is what we applied here. Okay, but it's the exact same proof with minor trivial modifications, which I think anyone viewing this video should be capable of. Okay, right, so axiom number 5 then, the final thing that we want to prove about multiplication is commutativity, okay, because we want to prove that it's not just any old ring, we want to prove that it's a commutative ring. Now, commutativity is again very trivial to show, so we want to prove that A bar multiplied by B bar is going to equal B bar multiplied by A bar. Okay, where of course this is multiplication in our quotient ring. So we want to show that it doesn't matter what way round you multiply two cosets from the quotient ring together. Okay, now why is this going to be true? Because multiplication in the initial ring is commutative. Again, the way we've defined multiplication in the quotient ring is utterly dependent on multiplication in the initial ring. Okay, so multiplying then A bar and B bar together. How does that work? Well, we take a representative from here, take a representative from here, and multiply them together in the initial ring. Okay, so this is now multiplication, green multiplication here, and then take the coset that contains that. So we've got A multiplied by B here. So that's the left-hand side developed. Now let's develop the right-hand side. So multiplying these two together, take a representative from B bar. Why not take the exact same representative as we chose here? So B, take a representative from A bar again, choose the exact same representative A. Multiply them together in the initial ring, so green multiplication here, and then take the coset that contains that. Now these two cosets are going to be exactly equal to one another because the two representatives are exactly equal to one another, because commutativity is true in the initial ring. So A times B with green multiplication is equal to B times A with green multiplication. Okay, so because of commutativity in the initial ring, you get commutativity in your quotient ring. Okay, so now we have successfully shown that our quotient ring, this set of cosets which we formed from the ideal inside the initial ring, with these definitions of addition and multiplication on, which are very, very natural, okay, just taking representatives from the cosets and adding or multiplying them together using the initial addition or multiplication rule from the initial ring. This does obey the axioms of a commutative ring if the ring that we started off with was a commutative ring, and so we have finished the construction of a quotient ring. Okay, so I think we'll have a break here now, and in the next video what we will do is firstly we'll discuss two special ideals that you can quotient any ring out by, so namely the zero ideal and the unit ideal, and then what we'll do is discuss the first isomorphism theorem for rings.